And so in this case, what we're going to do is learn how we can start to draw some basic conclusions from data using the standard deviation. The first thing I want to tell you is I've hinted before that the standard deviation was important because it tells you roughly a good chunk of your data should lie between one standard deviation. In other words, I think I've said to you before, if you have a classroom of students and the average or the mean is about an 80 and the standard deviation is 10 points, then that means that plus or minus one standard deviation around the mean, so plus 10 points minus 10 points around the mean of 80 points, most of our students should have scored in that range. So if your mean is 80, then somewhere from 90 to 70, most of our data should have fallen in that range. Most of our kids or most of our students should have grades that fall into there. But notice when you say the words like most of the data, it isn't very scientific. I was very careful to tell you that the standard deviation is telling you where a good chunk, most of your data lies, but I didn't quantify it at all. I didn't give you any concrete, facts with regard to that. Here we're going to cover those facts. I'm going to tell you exactly what percentage of people should fall between one standard deviation of the mean and then also two standard deviations and so on, so that you can kind of finally understand why this concept is useful to begin with. The first thing is I want to make sure you understand that everything I'm going to tell you in this section, it only applies to bell-shaped data, which is extremely common. Extremely common, and that's kind of an interesting thing by itself. If you go collect data on average, almost always it's going to be bell-shaped. And what I mean by that, let me give you an example of what bell-shaped data is, right? So if I have, taking the example of grades in a classroom because it's something we're all familiar with, if I have grades and if I have the number of students here, so this would be STU like this, then let's say I take an exam, and I figure out that the average value, the average grade of everybody that scored on this test was an 85, okay? So what bell-shaped means is that if you go and do this with a large enough class of any number of students, then what you're going to find is the data is almost always going to look like this. It's going to go up, and then it's going to kind of peak, and then it's going to kind of come back down. This should be symmetrical. I'm not a perfect artist, so you got to kind of bear that in mind, but it should be absolutely symmetrical about the mean. And what this means is that most of the data, you can see this is number of students up here. So the taller this curve is, it means the more people scored that score. Now, I'm not going to write it all down because I don't want to clutter this up, but over here, here's 85. So here you have 86, 87, 88, 89, 90, all the way up to 100. And here you have, 84, 83, 82, all the way down to the lowest grades that you have on your test, right? So that means that because of the peak of the curve is right on top of 85, that means that the mean is 85, right? But notice there's some spread to this data, right? The data is spread like this, but it's bell-shaped. That's what bell-shaped means. So in this section, when we are discussing standard deviation and when we're discussing this empirical rule, keep in mind that it only applies to bell-shaped data. There are certain special cases when the data you collect is not going to look like a bell-shaped, but in this case it will. So if you take this exam with enough people in the room, most of the people are going to score around 85 if that's the mean. A very small amount of people will score 98, 99, 100 over here. Very small amount of people will score low scores over here. And around the mean, notice on either side, plus or minus of the mean, you still have a healthy amount of people scoring just shy of 85 over here. This is 83, 82, 81. And you also have a very healthy amount of students scoring just on the plus side of the mean, 86, 87 over here. And as you get farther and farther from the mean, less and less and less students score those points, right? And so this is kind of a graphical way of showing you what I've been talking about all along with how spread apart is your data. In this case, this data is spread like this, but in a different classroom, the data might be very tightly compacted about the mean, where if this is the mean value here, then most of the data falls right on top of the mean and it falls off extremely sharply. Or you could have a different classroom where the mean is very broad like this. See, even spread out even more. So if this were the mean value here, then this would be a classroom with lots of variation, a large standard deviation about the mean on both sides of the mean. Very large standard deviation. That tells you that this curve is spread out really far. That's what this one would be. But if you have a very sharp peak about the mean, this is a very small standard deviation because it tells you that most of the data is packed around the mean. All right, so what we're going to do in this section is quantify that. What does it mean to say that I have a standard deviation of 5, right? How can I really use that? All right, so what I'm going to do then is introduce something called the empirical rule for standard deviation. And what I mean by empirical rule, it just means that it's a rule of thumb. That's really all it means. This could just say rule of thumb for standard deviation. So don't worry too much that it says empirical rule, all right? So this is kind of the bread and butter of statistics. What this says is about 68% of the data lie within one sigma, one standard deviation of the mean. You need to get used to the idea. When you see a small sigma like that, you need to read it as standard deviation. So when you see this, you plug in standard deviation. This is incredibly important. This one sentence on the board summarizes a lot of statistical theory, and so you need to make sure you understand it. If you have a data set and you know that it's bell-shaped, which most data is, about 68% of the data lies within one sigma, one standard deviation of the mean. So that means that if I have a mean of 85 and I calculate, because I know how to calculate the standard deviation, and I get a standard deviation of plus or minus 10 points, then that means that between the ranges of those grades, plus or minus 10 points around the mean, about 68% of my data is going to fall there. So now I'm putting a number on it, you see, because before I told you, yeah, most of your data is going to lie in one standard deviation of the mean. And I kept telling you that over and over because I didn't want to bog it down with this kind of conclusion so early on. Now I'm giving you a number. I'm telling you that if you know the mean and you know your standard deviation, then pretty darn close to 68%, which is well over half of the data in your entire population, is going to actually lie within one standard deviation of the mean. So it's a conclusion. It's a rule that tells you how important the standard deviation is. If I have a classroom of 200 people and I know the mean and I know the standard deviation, then I'm immediately going to know the range of values that about 68% of my students are going to lie within. That's how important the standard deviation is as a rule of thumb. Okay, so we can take this one step further. About 95% of the data lie within 2 sigma of the mean. 2 sigma. So standard deviation is called sigma. So when you talk about 1 sigma, you mean 1 standard deviation about the mean. So for instance, if the mean value of the grades on my exam are 50 and my standard deviation is 5, then 1 sigma is going to be from 55 down to 45. That's plus or minus 5 about my mean. If my mean is 50, my standard deviation is 5, then 1 sigma is going to be plus or minus 5 about my mean. All right? That means 68% of my data is going to fall in that range. Right? But it also means that 2 sigma, which if my standard deviation was 5, then 2 sigma would be 10. Okay? Plus or minus 10 about that 50 is an average value, so down to 40, up to 60. That's 2 sigma about the mean. Then I know that 95% of my data is going to lie within 2 sigma. So if I have a classroom and I know the mean and I know the standard deviation, then if I go out 2 sigma, a little bit farther on either side of my mean, then I know that 95% of the data is going to lie within 2 sigma. All right? And finally, we're not going to go any farther than this, about 99.7% of the data lie within 3 sigma of the mean. So again, if the average value on my exam is 50 and my standard deviation is 5, then 3 sigma would be 15. 3 times 5 is 15. 15 points on the plus side of my mean to 15 points on the minus side of my mean. 99.7 of my students are going to score within 3 sigma of the mean. So that is really all that these empirical rules are saying. And I know that they're a little kind of hard to read because they're a little jumbled together, but I'll break them up. Right? So you have 1 sigma, 68% falls in 1 sigma. 2 sigma means 95%. 3 sigma means 99.7%. So let me kind of drill that in with a picture, because a picture really is worth 1,000 words. So if I have, for instance, a bell curve, right, like this. So try to draw a nice little bell curve. If the middle of my bell curve is always my average value, right, so I'm going to put a sigma, a mu there, because that's the average value that I have, right, then 1 sigma would be up here and minus 1 sigma would be there. That means that means 1 sigma on the plus side of my mean and 1 sigma on the minus side. So if I had to put numbers, if the mean of my exam is 50, and 1 sigma would be, 10 points up here and 10 points below the mean. That's all it is bracketing it. Then what it really means is that if I look at this guy like this, right, and if I shade this, then what this means in this particular case is that 68% fall inside this range. 68% fall inside of plus or minus 1 sigma about my mean. In a graphical way, this is saying exactly what we wrote down here, right? So if I draw another one, trying to make it look real similar. They're not going to look perfect. If this is the mean value, mu, then this would be 1 sigma. This would be -1 standard deviation over here. I'll go ahead and put this guy as 2 sigma, and this is -2 sigma, so 2 standard deviations. So that's twice as far out from my mean. That's what that means. Then if I go and look at this shaded region, notice it's a much larger region, because what I've decided here is that 95% fall in this range. 95% of my students fall in this range because it's a wider range, about the mean, right? And then the last thing would be to draw this guy like this. This would be my mean. This would be 1 sigma. This would be 2 sigma. This would be 3 sigma. This would be -1 sigma, -2 sigma, -3 sigma. So 3 standard deviations, plus or minus, about my mean, right? Almost the entire curve is here. So that means 99.7% of my data is going to fall between plus or minus 3 standard deviations. So think about it in terms of a classroom. A grade of 50, standard deviation of 10. So I'm going to go 10, 20, 30 points on the plus side, 10, 20, 30 points on the minus side, about my mean. 99.7% of my students are going to fall between 3 standard deviations around the mean. Notice the curve has a tiny little portion on either side here. These are the people that did so well that they did even better than 3 standard deviations. These are the people that made like a perfect score, or people that made like a 0, that just didn't even try, guessed randomly. So if you have a truly random, and students taking exams are not random. Some are going to know more and some are going to know less. So we're not arguing that it's random when they take an exam. But if you take an exam with enough students, you're going to find that most of the students are going to land here around the mean. Some are going to do better, and as you go up, up, up in the grades, less and less and less students are going to score those scores. And if you go low, low, low in the grades, less and less and less are going to score those. And these standard deviation empirical rules apply. So let's see how we could use this in a quick problem. And then what we will do is, in the next section, we'll have some more problems. So let's go ahead and apply this now. The average weight of a newborn baby, or of newborn babies, I should say, born, is bell-shaped with a mean of 3,325 grams, so 3,325 grams, and a standard deviation of 571 grams. What percentage of newborns weigh between 2183 grams and 4467 grams? All right, so the first most important thing for you to pull out of this is that it says the average weight of babies is bell-shaped. That's a huge clue that you need to think, okay, the standard deviation empirical rule applies that we just learned. They give the mean, and they also give the standard deviation, right? So let's see if we can figure this out. Let's go and draw, you don't have to do this for every problem, but I think we're still learning this stuff, so let's go ahead and draw it here. So here is a bell-shaped curve, just to kind of make sure you understand this. And it tells us in the problem that the mean is 3325, and it's in grams, so I'm not going to put the G for grams. But this is the mean. This is most of the babies that are born with that weight. But it gives us the standard deviation. It tells us that the standard deviation is 571 grams. So over here I'm going to write the mean is 3325. The standard deviation is 571 grams. All right? So what this means is that if I want to go figure out what is one standard deviation about my mean, right? What is one standard deviation? Well, if I'm looking at one standard deviation, I would take my mean plus one standard deviation. If I take these numbers and add them together, I'm going to get 3325 plus 571. That's plus one standard deviation. And so what I would get when I add these together is 3896 grams. And then on the minus sign, take the mean minus one standard deviation. I'm going to have the mean 3325 minus 571. So if I do this subtraction, what I'm going to get is 2754 grams. So what this is telling us, if I were to represent this on the chart, is that 1 sigma on the plus side, I don't have enough room to write it, so I'm going to do it down here, is, I'm going to say 1 sigma is 3896 grams. And on the minus side, right, I'll say minus 1 sigma. So 1 sigma on the other side of the mean is, I just calculated it, 2754 grams. So what I've done is I know the mean, I know the standard deviation, so I can immediately say, okay, what is 1 sigma? The mean plus 1 standard deviation, the mean minus 1 standard deviation. So I do the plus and minus, and I figure out that 1 standard deviation about the mean would be between 2754 and 3896 grams. And I go back to my problem, and it says, what percentage of newborns weigh between 2183 and 4467 grams? Now this 1 sigma, these numbers don't match anything in the problem. I'm trying to find what percentage are between 2183 and 4467. So clearly it's not 1 sigma, right? So let's go and see if we can do 2 sigma and see what happens. So let me switch colors. And then I'll say, all right, I'll say, what is the mean plus 2 sigma? So what this is 3,325 plus 571 plus another 571. So you're adding 2 times sigma. And when you get that, you get 4467 grams. And if you do on the minus side, minus 2 sigma, it's 3,325 minus 571 times 2. And what you get is 2183 grams. Now these numbers actually match our problem numbers. So 2 sigma, here would be the next one, right? 2 sigma equals 4467 grams. And on this side, 2 sigma equals 2183 grams. So that means I'm looking for what percentage lies in here, which is everything that lie within plus or minus 2 sigma about my mean. These numbers here match in my problem. It says, what percentage of newborns weigh between or have a mass between 2,183 grams and 4,467 grams? It just so happens that these numbers that we're asked to figure out what percentage lie between are exactly 2 sigma, 2 standard deviations on either side of my mean. So I go back to my empirical rule, and it says right here, about 95% of the data lies within 2 sigma of the mean. So because the boundaries that we're asked about are exactly 2 sigma, then we know that 95% of babies weigh or have a mass between 2183 grams and 4467 grams. This is the answer. The only reason we're able to do this problem, the only reason, is because they told us the mean and they told us the standard deviation. And the range that they asked us to go figure out what percentage lie between happen to be exactly 2 standard deviations, 2 sigma plus or minus the mean. The way you figure that out is you go and you literally add 1 standard deviation and subtract 1, and you figure out that the endpoints here are not what we were asked to figure out in the problem. So then we do it again with 2 sigma, and we figure out that these endpoints actually are exactly the endpoints they're asking us. So because it all lines up, we're able to use our empirical rule, and we're able to figure out that 95% way between these ranges if the mean and the standard deviation are given as shown. The drawing I did here was mostly for your learning entertainment value, right? I mean, you have a mean, you have a 1 sigma, and you have a 2 sigma, and I'm trying to get you familiar with that idea, so I'm drawing pictures, but really, and to do this problem, all you need to do is figure out that this is 2 sigma plus or minus the mean, and once you know that, you know it's 95%, you're done, circle the answer. So, we've covered a lot of material in this section. The empirical rule for standard deviation is important because it tells you how the standard deviation can be used. 1 sigma, which is this guy, plus or minus the mean, 68% of the data fall between there. It's a good benchmark if you look at 1 sigma to get a good rough that more than half of your data is going to lie between there. If you're looking in between plus or minus 2 sigma around your mean, then almost all of your data is there, 95%. And if you're looking at 3 sigma, then darn near every data point there, 99.7%, is going to lie between there. That's why we calculate standard deviation. That really is the reason. Because I can tell you the standard deviation, and you're immediately going to know, all right, well, 68% of the data is going to be between 1 standard deviation around the mean. Or in between 3 sigma, 3 standard deviations, almost everybody in the data set is going to lie there. So it's a great way to summarize data. It tells you how much your data is spread, and it lets you draw some basic conclusions. So let's wrap this section up. Make sure you understand this. Follow me on to the next section. We're going to continue working some additional problems with using this empirical rule to give you more practice. It's going to be very similar to what we've done here, so don't expect them to be a lot harder, but they are going to give you more practice. Learn anything at mathandscience.com.